we looked at the Stephenson mechanism, which we saw could not be analyzed by the velocity difference method if link 6 is the input, okay, then I don't have enough information about the path of point C to be able to solve my vector equation involving the velocities of C and D, right? So because if I write velocity of C equal to velocity of D plus velocity of C relative to D, then I have no idea about the motion of C. I know neither the magnitude nor the direction. Okay. Therefore, this vector equation now has 3 unknowns and cannot be solved. Okay. So, what we did last time was we looked at instant centers, using instant centers, and we were able to solve it for by using instant centers. So that's another option to try to solve, but in some cases or in some configurations of the linkage, the instant center may be outside your working area, and it may not be you may not be able to use that method either in order to solve for the velocities of this linkage. So there's another method called solution by inversion, which is used for cases like this, where if the driver link, so here the driver link 6 is not part of a 4-bar loop that contains the frame. If that is the case, then we saw up here that it is not possible to analyze the linkage directly using the relative velocity or velocity difference method. Because the vector equation cannot be solved for 3 unknowns. In such cases, we can solve it using the previous techniques, but we make a change. So what we do is, in the same linkage, if I make O2A link 2 or link 4 the driving link, okay, instead of link 6 being the driving link, I invert the linkage to make something else the driving link, okay. And then, because if you look at it, all the angular velocities, if you look at the way we drew, when you look at the velocity relations, they are all linearly related to the input angular velocity. Okay, all the angular velocities in the linkage are linearly related to the input angular velocity. Okay, so we use that fact, we change the driver link, because all the link angular velocities are linearly related to the input angular velocity. So let's say I say let omega 2 equal to 1 radian per second. Say count it. Okay. Instead of omega 6 being my input, I say omega 2 is my input. Now can I solve the linkage? Straightforward, right? Because I can find this is a 4-bar loop with the frame as one of the links in the loop. I can solve for velocity of B, velocity of A. By image, I can find the velocity of C. Once I know the velocity of C, I can find velocity of D and all the omegas. Now, whatever omega 6 I get, I just have to scale it by what my original omega 6. So I scale everything accordingly. And I can solve for using the existing methods. Okay. So this is solution by inversion. It works for, so if a mechanism can be solved, by inverting it. So if the original mechanism, so it's called, if it's not easily solvable, if this equation by the velocity difference method, it's called a kinematically complex mechanism. Okay. So the mechanism they say is a kinematically complex mechanism because you don't know the path of some points that you require as you apply the velocity difference method. If by inversion you can convert it into a simple mechanism, it's called low degree of complexity. Okay, so in this case, if I can solve by inversion, I can say that this mechanism has a low degree of kinematic complexity. We'll encounter some mechanisms where even by inversion I cannot solve it using the velocity difference method. Yes?
The same links are staying fixed and the same links are staying movable. So it is not an inversion.
So inversion is I'm using something else as the input link. Our original definition of inversion was we fix something else. So it's the same thing. It's just, you're not changing the fixed link here, but you're changing the input link. So inversion has a slightly different meaning here. Okay, you're essentially changing the input link. So with this here, now you solve for omega 3, omega 4, omega 5, omega 6, and knowing actual omega 6, which is the input, scale the other angular velocity. Okay, so this is the method of inversion which you could use to solve certain mechanisms. We will look at another method that is quite useful even for mechanisms with a high degree of complexity. It's a versatile method called the auxiliary point method. This can be applied to most complex mechanisms, all simple mechanisms and most complex mechanisms, and it's based on this auxiliary point method for velocity analysis. So let's look at that now. Okay, so suppose you have two links that are connected by a revolute joint, right? Which is what we encounter all the time. Okay, and it's based on this basic principle. So say I have a line, okay, passing through that. So these joints are called the motion transfer points, because that's where motion is transferred from one link to another. Okay, so the joints are called the motion transfer points. So say this is body I and body J. Now suppose I know the velocity of some point A, okay, on body I. Okay, say I know this velocity. Okay, I draw what's called an auxiliary line joining point A and B. Okay, B is the motion transfer point to link J. From I to J, the motion is transferred through joint B. Okay, so I draw line through this. Now, so B is a point on link I and it's also a point on link J. Okay, so if I take the projection of this velocity, so I take the component of velocity along this line I. Okay, now because A and B are points on the same rigid body, okay, I can say that the component of velocity of B along this direction is going to be equal to this. Makes sense, because A and B are on the same rigid body. Now let me take a point C on this auxiliary line, but which lies on J. I can also say, because again that same velocity is transmitted, right? So I have velocity of C, velocity of B, and this is also equal to velocity of C along I. Okay, so I know one component of the velocity of point B and of point C. So that means if I draw a perpendicular to that, right, the actual velocity of B, its head necessarily lies on this perpendicular, right, because I can split it into two perpendicular components. I already know one component. Okay, so if I have some additional information, I know that this, so if I know two components along two different directions of the velocity of B, then I construct perpendiculars to those two components. Wherever they meet, that will give me the head of the velocity, actual velocity vector of that point B. Okay, that's the principle similarly for velocity of C. So let me just write down a couple of things and then we'll do an example to make this. So this is the basic principle. Say two bodies I and J are connected the component of velocity VAI, sorry, VA1 along the line AB equals the component of because I is a rigid point. Similarly, one C1 body J located on so this AB is known. Okay. Then the tip of vector BC necessarily lies on the normal to BC. Okay, so that would be here. Call this line XX. Okay. So if for a point we know two such components, the tip of the point's velocity vector will lie at the intersection of the two normals at the tips of the known components. Okay. So if I can find the velocity of two such points on a link, then I know everything about the velocity of that link, right? Because if I find the difference, then I know the omega of that link. Okay, so if you know the velocity of two such points, let me just draw the two links, or we'll do an example actually. So let's just say the line AB, that's called the auxiliary line. Okay, so I have link I connected to link J, motion transfer point, point A. Question?
How is the auxiliary line drawn?
Yeah, so if I know the velocity of point A, okay, or I know the component of the velocity, okay, we'll see in a second when I do an example. Let's just say I know the velocity of point A, okay, and if I know this, I can take any line through A and B and do it like that. But in some cases, I may not know the full velocity of A, but I will know a certain component of A. So in that case, I will draw it along that component which I know. which we will see when we do the example. So in this case, in the general case, like I could essentially take line passing through A and B. Okay, and C would be another point that I take on the same line. Okay, so let's see, where were we? Okay, so auxiliary lines are the lines drawn through the motion transfer points of a floating link along which the velocity components are known. Okay, and auxiliary points are points on the floating link at the intersection of two auxiliary lines. This will be clearer as we do an example. So let's consider.
Will this still be true if the point B is fixed?
If it is fixed to a wall, no, then it's not transferring motion, no? It's a motion, yeah, it's a motion transfer point. So let's say we have a floating link, a ternary floating link. Okay, or wait, let me call this PQ. Okay, I have a ternary floating link and I have a point A, okay, whose velocity I know. Okay, so I take an auxiliary line that passes through A and B. Okay, some auxiliary line that passes through A and B. Similarly, I may know the velocity or a velocity component of point B. Let's just say I know the velocity of point B. Okay. So I take another auxiliary line passing through this motion transfer. So awful line. That's better. Passing through this other motion transfer point for this ternary link. And then let's say I have a third point C, whose velocity I know again, and I take my third auxiliary line through that point. Okay. So I need only 2 points to completely define the motion of the link, right? So let me say that, say, x and y are my 2 auxiliary points. If they lay outside, you will assume that they still lie on the coupler link. Okay, here I got my intersections for x and y inside this boundary PQR, but they could very well lie outside that. But it is still considered a part of this floating link for the purposes of analysis. Okay, so actually let me draw one of these slightly better so I can.
You and I have 3 different motion points and
Motion transfer points, yes. So it's a ternary link. It's a ternary link. It's a ternary link. So it's connected to 3 different links. And let's say I know something about the velocities of, let's say, in this case, let me say I know the velocities of A, B and C. And I want to find the velocities of these auxiliary points. Just draw it like that so I can show you that y can be outside. It's not necessarily that. Okay, so this is point C, whose velocity. Okay, so now I have, since these are known, I know the components. Okay, this would be VA along I. This would be VB along 2, should be 1 actually. And I have VC along 3. I know the velocities in those directions. So now if I move this to this point x, the velocity of x will be equal to this velocity Vx along I equal to VA. Sorry, Vx along 1 equals VA along 1. The auxiliary line 1. Okay. Similarly, I change the lines. Okay. So this is, ignore this one. Okay. So those are my 2 auxiliary points. Save this. This thing is misbehaving today. Okay. So I have x. This is Vx along 1. Right? Which is equal to VA along 1. Now, this tells me that the head of the velocity of x should lie on the line that is perpendicular to this. So let me look at, I need one more component. Okay. If I look at this, x also lies, because x lies at the intersection of 2 auxiliary lines. So if I look at line 2, I do know another component of velocity here, right? So here I have, so let's say this is VB along 2, then velocity of x along 2 equals VB along 2. Okay, and I know that if I construct a perpendicular to this, what would this point be? Velocity of x. Okay, so this is the velocity of x. Okay, because I can either split it into a component. So I'm splitting it into two perpendicular components. So I know, okay, I know components along two directions, which means this vector will be at the intersection of the perpendiculars to those two components. So that gives me the velocity of x. We look at velocity of y. Velocity of y, one component is the same as along 1 is the same as the velocity of a along 1. Here, because my intersection with 2, I need a third, so here I take VC along 3. Okay, so if I look at the velocity of y will lie somewhere on the perpendicular to Vy of this. Then the other component, we call this that's going to be this. VC along 3. Okay. Therefore, now I can construct the other perpendicular to this, which means this gives me the velocity of y. Okay, I know the velocity of x, I know the velocity of y completely now, which means I know the angular velocity of this ternary link and the velocity of any other point on the ternary link. Okay, we'll apply this now to that same example that we did. Okay, with omega 6 as the input without doing inversion. Let's see what it does, how we can solve it using the auxiliary point method. So this was our problem. Four, 5, 6. Okay, so for what points do I know the velocity or velocity components? Here, I know omega 6. Okay. So I know the velocity of d completely. Right? I know the velocity of d. I know magnitude and direction for the velocity of d. So my ternary link, my floating link here is ABC. Okay, and because I don't have enough information about C, I'm not able to apply the velocity difference method. Okay, that's why instead of inversion, I want to try using the auxiliary point method. I haven't, let me not draw all these in a straight line like this. Just to differentiate. Okay. So let's say this is my velocity of d. Okay, so now I have to pick my auxiliary lines, right? I can pick one through D and C. Okay, so I take that could be my auxiliary line 1. Okay, now this is in the previous case I said I know the velocities of 3 points. In this case I know the velocity of only 1 point. How do I pick my other auxiliary lines? I already gave you a clue. No. Look at the other motion transfer points, A and B. They are both connected to links that are pivoted to the ground. So which means along the link, do I know anything about the velocity? 0. Because for A and for B, the velocities are necessarily perpendicular to those two, which means that component that's transmitted along the link is 0. So I do know something about the velocity that's transmitted through the motion transfer points. So I can take my second auxiliary line through that and the third auxiliary line through this. It's almost passing through C, but okay. So now I know my two auxiliary points. I can say these are X and Y. It's almost passing through C, but that was unintentional. Let's see if I can just change that. Okay, slightly better. So I have X and Y as my auxiliary points. And I have 0 velocity being transmitted through A along O2A and through B along O4B. Okay, that's what I'm using. So I don't need to know the complete velocity vector for these points. As long as I know a component, I take my auxiliary line through that component in order to construct my auxiliary lines. Now I have velocity of D along 1, right? That will be also the velocity of Y along 1, right? So one perpendicular for the velocity of Y will be perpendicular to this, right? The other velocity that's being transmitted is 0, which means the other perpendicular will be perpendicular to the line 3, right? So this is okay. It means that velocity, the absolute velocity is necessarily perpendicular to that line. So that now completely defines. So wherever it intersects this other perpendicular, this gives me the velocity of Y. Okay, because this is perpendicular to this, that means the component along 3 is 0, which is what is being transmitted. For point X, same thing. I do Vx along 1. So Vx along 1 is Vy along 1, Vd along 1. Perpendicular to this, it has to lie, the velocity vector lies on that, the tip of the velocity, sorry, the head of the velocity vector or tip, and the other one is perpendicular to this, right? So this is perpendicular to 2. That would be the velocity of X. Okay, so this is the auxiliary point method, and it's applicable to most mechanisms you can analyze by this method, regardless of their complexity. And the complexity arises because you have a floating link that is typically ternary or higher order, right? So when the coupler link, the floating link, is a ternary or higher order link, it induces complexity in the mechanism, and the auxiliary point method is a very versatile method for analyzing these kinds of mechanisms. You can modify the method. You can modify the method. You may want to check Ghosh, Malik, Dittrich, that book, to see if they actually have an example where they have a prismatic joint. Yes.
But evaluating the velocity, they kind of trap, right? You can only find out the velocity at points that happen to be auxiliary points. How do you use this data in?
If you know the velocity of, so when I say this is X and Y, and I say my ternary links includes, so I am doing the analysis on the basis that this x and y are included in this ternary link.
After this, you do something.
So after this, exactly, after, so I'm not, yeah. So once I know Vx, Vy, okay, how are they related? I can write Vy is Vx plus V of y relative to x, right? So the difference between these two velocities is directly equal to omega of this linkage times xy. So omega of this link, let's just call it omega 3 here. Omega 3 is Vy minus Vx by xy, right? Here vectors Vy minus Vx by x. So I know omega 3. Once I know omega 3 and the velocity of any point on a link, velocity of any other point on the link is, I just keep applying this equation. Or by image, I just construct the velocity image for that link. So I need two velocity. If I'm looking at, so to completely define the velocity of a rigid body, I need the velocity of one point and its angular velocity, or I need the velocity of 2 points, because I know the distance between those 2 points. Okay, so the velocity, this method gives you more information, because you're actually solving for 4 quantities, Vx, Vy, the x and y components of 2 velocities, the velocities of 2 points, whereas degrees of freedom wise I only need 3. I need the velocity of 1 point and the angular velocity of the link, but the method gives you the velocities of 2 points, from which you can now determine the angular velocity and hence the velocity of any other point. Okay, all right.